Hello everyone. In this video, we are going to cover chapter 12, section 12.6. In section 12.6, we are going to look at kinematic equations for projectile motion. As you recall from your physics classes, projectile motion, normally we're going to break it into two components, the horizontal component and the vertical component. There are many different applications for the projectile motion, but just to refresh your memory, projectile motion horizontally, it's constant velocity. Vertically, it's free fall. The reason being, when an object is under projectile motion, the only force being applied to the object is only the gravity. And that means the only acceleration being applied to the rigid body will be the gravitational acceleration. So, and that gravitational acceleration will always be pointing down. So that means horizontally, I'm not accelerating or decelerating. The velocity on the horizontal direction will always be the same. It's constant velocity on the horizontal direction. And then vertically, we have free fall. Vertically, on the vertical direction, it's free fall. Okay, here is a visual illustration of what we just talked about. Yellow bar represents the actual path of the particle under projectile motion. The red one shows what's happening only on the vertical direction. As you see, vertical direction in between the rows, every single one of the row in between the rows represents every same amount of time segment. Let's say 1 second, for example. That means as the time goes by, with the same time of with the same amount of time increment, you see more distance on the vertical directions only. Vertically, I have acceleration, gravitational acceleration pulling it down. The velocity is going bigger along the vertical direction coming down, and you have more distance to travel every as the time goes by, more distance to travel. Horizontally, it's constant velocity. Horizontally, the same segment, the amount of distance that we're moving will be the same horizontally. Horizontally, it's constant velocity. Vertically, it's free fall, it's constant acceleration. Okay. As we talk about AX equal to 0, it's the velocity on the horizontal direction remains constant. Vx equals the original velocity on the horizontal direction. And then vertically, okay, vertically, you have free fall. Since we got free fall, that acceleration on the vertical direction equals the gravitational acceleration, and it's going down. That's why it's negative g, because we define positive going down, positive going up. Okay, so ay equals negative g. These are the three master equations relating the velocity, the position, and the time together. Now let's take a look at some examples together. Example number 1 says, if I have an initial velocity VA, which is 10 meters per second, and I know the angle that is 30 degrees, we're looking for the horizontal distance to travel in the velocity VC. We know that horizontal distance is going to be velocity times time. Velocity is constant velocity. Okay, multiply the amount of time that we need to the entire time going from point A to point C. So if we know the horizontal velocity, which we do, we know VA equals 10, and then that 30 degree, we can break that 30 degree into cosine 30 and the sine 30. Cosine 10, cosine 30 gives me the horizontal component VAX, and then 10 sine 30 gives me the Y component, right? We know the horizontal component of my initial velocity. In order to find the distance, all we need is the amount of time. How much time does it take going from location A to location C? That would help us define the horizontal distance. Now, how do we figure out how much time does it take? Keep in mind that even though horizontally and vertically we separate what's going on, right? Horizontally, constant speed, constant velocity, vertically, free fall, constant acceleration. Even though we separate the horizontal and the vertical, keep in mind that horizontally and vertically, whatever is going on is happening at the same time. What it means is that the amount of time that we spend doing the horizontal motion will be the same as the amount of time that we spend doing the vertical motion. Okay, so keep in mind, this is the key. Horizontally, vertically, we share the same amount of time. Okay, so Vx is tan cosine 30. This thing does not change throughout from A to B to C. Horizontal component does not change. And then vertically, we got our Vy. Vy equals tan sine 30 minus 9.8 and 9.81 t. Okay, this is coming out from our first master equation right here. Initial vertical velocity we know, and then minus the g gravitational acceleration times time. Okay, so that's that equation. X, this represents the position. Position, how much distance does it travel horizontally, will be the horizontal velocity times time. And then vertically, how much does it travel? It will be this equation right here, the second equation right here. Okay, so that refers to since we have y0 equal to 0, initially no vertical distance, we have v0y times t. You have tan sine 30 vertical component of the t, vertical component velocity times t minus 1 half 9.81 t squared. Okay, so these are our equations, horizontal and vertical velocity and position. We know that y equal to 0 at c, see y vertically, see right here, c is down here, okay? At c, y equal to 0. So we set this equation, last equation right here, set this equation to be 0 and solve for the value of t. Notice that you have a t squared. This is a quadratic equation. From our algebra class, we know that for quadratic equation, we got two solutions for this I know because it's a quadratic equation. So t equal to 0 and then also 1.019 second. And notice that these will be the two. At location A, you also have a y equal to 0. So at point A, you have t equal to 0. At point C, you have the 1.019 second. So at point A, at point C, that is our time in order for the t equal for the in order for the position equal to 0. Okay, so we know that t equal to 0 will be at point C at point A, t equal to 0 at point A, and then t equals 1.019 at point C. Okay, so overall we're going to use this time, okay, this 1.019, that will be an amount of time it's needed going from point A to point C. Okay, so we take that time, multiply by the initial velocity. Okay, initial velocity, horizontal component, multiply the amount of time. That gives me the total horizontal distance traveled. Okay, next thing, we also are looking for the VC. Okay, VC, we have velocity c, horizontal component, as we say, no change, still tan cosine 30. That's the horizontal component of the VC. Vertical component, plug into the equation. It's this equation right here, the first equation right here, this one right here. Plug in the initial vertical velocity minus g times t, and that t is going to be the t, that span going from A to C. Plot that in, we got our vertical component at VC. Okay, putting these two together using our Pythagorean theorem, you got 8.66 squared plus negative 5 squared, and taking the square root, that gives me the magnitude of the VC overall. Next example, projectile motion. We file this particle at point A with the initial velocity 150, and we have this 3, 4, 5 triangle. And keep in mind that 3, 4 triangle tells us, how slant where the VA is. It doesn't tell us the angle directly, but I know that the rise over run vertical component of the initial velocity VA versus the horizontal component of the initial velocity VA will be 3 over 4. We know the proportion. We're looking for the horizontal distances travel. Again, we need the velocity horizontal component, we know, and then we also need how much time does it take, right? How much time, velocity times time gives me horizontally how much does it travel, and then the time in the air. So keep in mind that how much time we travel in the air, it's the same. Horizontally, how much time does it take, and vertically, how much time does it take, will be the same thing. Now, let's take a look. We're going to break it into horizontal motion and the vertical motion. Horizontally, as we talk about, horizontal component of the acceleration, it's the 4 over 5 times 150. And then the range, total range will be 120. So 150 times 4/5 gives me 120. 120 times TAB will be the horizontal range. Leave that there. We don't know how much time it is, but let's figure out how much time does it take from the vertical vertical analysis. Vertical motion, free fall. Plug into the equation. This is the position equation. That's our second one in our master equation, which is this one, second equation right here, relating the position, velocity, and time together. Okay, in this position, we know that YB is negative 150. Look, starting from right here, and at location B, it is 150 meter below the initial position. So we know that YB over here, negative 150. YA initially as 0, right here, we define over here as location A as a point 0. VAY is the vertical component of that VA, so you have 150 multiplied by 3/5. That gives me the vertical component of that velocity, initial velocity. And then plug into to this equation right here. We got that, right? And again, it's a quadratic equation. We can solve for the value of t. Quadratic equation, we solve for the value of t. And that t, only one of them makes sense. TAB first, and then TAB 19.89, right? So we're gonna so that means the amount of time from A to B takes 19.89 seconds. We're gonna take that value, take that second, take that much amount of time, plug into this equation right here to help us figure out horizontally how long, what's the range, how much does it travel. Okay, so we get 2387 meters on our horizontal range. And let's take a look at another group problem together. We have a skier leaves the ski jumping at RAM theta A equals 25 degree, and it hit the slope at B. We're gonna figure out what's the initial velocity VA. Again, we're gonna break it into horizontal and vertically. Horizontally, constant speed. Okay, we have the horizontal component of that VA. So it will be 4 over 5 times 100. So 4 over 5 is 4 over 5 times 100. Hold on. 4 over 5 times 100 is the horizontal. That's not the velocity. 4 over 5 times 100 is the, it's the horizontal. Look, it's that 100 horizontal component of that 100. Notice that this thing comes down. Now we're looking at only the horizontal. How much distance do we travel horizontally? Distance, we're looking for distance, is that 100 times 4 over 5. Now, right-hand side, starting with the initial position at 0, and you have VA times cosine 25 TAB. VA times cosine 25 TAB. Okay, horizontal component of the VA times the amount of time does it take. So we're going to write that TAB in terms of VA. And then vertically, what's happening? Vertically, it's free fall. Okay, this is our second master equation, plugging everything we need. YB equals negative 64. YB equals negative 64. That's going to be that YB negative 64 equals 0 plus VA. This is the Y component, initial velocity Y component, and then plugging the value of T. This one is coming out from the previous step. We're going to write that T in terms of VA. Same thing down back here, 1/2 GT squared. And using this equation, we can calculate the velocity, which is 19.42. And we can plug in to our first equation. If I know the total over here, 19.42 for the velocity VA, and then using this equation right here, 88.27 divided by 19.42, that gives me how much time does it take to finish the whole process from point A to point B. Okay, now back in here, I was paused over here. Where does that negative 64 comes from? If you get confused, if you're like, well, isn't that vertical component is going to be 3 over 5 times 100, right? Yes, that is correct. 3 over 5 times 100 should give us 60, but where's that 4 comes from? And keep in mind that you got 4 meters over here. Vertical is, so the vertical, how much you travel, it will be vertical component of that 100 plus that 4 meters up here. So that's 60 plus 4. That's where the 64 comes from. It's negative because we define location A as our 0 position, and it's negative 64, meaning 64 meters below that position A. All right, so last group problem together. There's a golf ball right here. We're hitting the golf ball. We know the initial velocity of 80 feet per second. We're looking for the distance d and where it will land. Again, we're going to break our motion into a horizontal component and a vertical component. Horizontally, distance will be d cosine 10. Horizontally, right hand side, it will be velocity times time. Velocity will be 80 cosine I, this 55 right here. Be careful. Look, you have a 45. It's in between the ball and the slope of this, the golf ball, the surface. And there's also a 10-degree right here. So it's 45 plus 10. That's why it's cosine 55. Okay. And that times time, we can write TAB, time, write time in terms of distance. Okay. And then keep in mind, vertically, we have free fall. And this is our second master equation. We can plug in vertically what's going on. The distance is going to be d sine 10 degree. D sine 10 degree gives me the vertical distance. And then YA equal to 0. And then we have a velocity 80 sine 50, that gives me the vertical component of the initial velocity times time. Remember from the previous step, we are writing time in terms of distance, and you plug in the time here one more time. Okay, solving this equation, we have only one unknown. We can solve for the value of d. Okay, and solve for the value of d. And again, quadratic equation, we got two solutions. Only one of them makes sense. The non-zero one makes sense. So it's 165 166 feet for the distance right here. Okay, so that is the total distance from A to B at an angle of 10 degree. Okay, that's all I want to share with you in this video. Thank you for watching.